You're sitting still right now listening to this, but according to physics, you're actually traveling through time at the standard rate that defines our normal experience of time. And if you got up and started walking around the room, you'd be traveling through time slightly slower. Speed up to highway speeds? Even slower. Get close to the speed of light? Time would crawl to an almost complete stop. This isn't science fiction. It's measured reality, and the reason why breaks everything you think you know about time itself. Let's start with something that seems obvious but isn't. What is time? For most of human history, we thought time was like a river, flowing at the same rate everywhere in the universe. Isaac Newton described it as absolute, ticking away uniformly whether you're on Earth, on Mars, or floating in deep space. A second here equals a second there. Period. But here's what Newton didn't know. Time isn't separate from space. They're woven together into something called space-time. Imagine it as a four-dimensional fabric that makes up reality itself. Think of space-time like a giant trampoline. When you place objects on it, they create dips and curves. The heavier the object, the deeper the dip. Now here's the part that'll blow your mind. Everything in the universe, including you, is always moving through space-time. But you can think of this motion as being split between moving through space and moving through time. When you're sitting perfectly still in space, you're moving through time at what we consider the normal rate. But the moment you start moving through space, something has to give. The faster you move through space, the slower you move through time compared to someone who stays put. It's like a cosmic trade-off that governs everything in existence. This isn't just theory, we can actually measure it. Atomic clocks, the most precise timekeepers humans have ever built, tick at different rates depending on how fast they're moving. Back in 1971, two physicists named Hafele and Keating literally flew atomic clocks around the world on commercial airplanes. When they compared these traveling clocks to identical ones that stayed on the ground, they found exactly what Einstein's theory predicted. The flying clocks showed different times because their motion had actually affected time itself. The eastward flying clocks lost time while the westward flying clocks gained time. They'd proven that time itself had been stretched and squeezed by motion. So how does this actually work? Let me show you with what physicists call a light clock. It's the simplest way to visualize what's happening. Picture a clock made of two mirrors with a beam of light bouncing between them. Every time the light completes one round trip, mirror to mirror and back, that's one tick. Now, let's put one of these clocks on a spaceship and keep an identical one here on Earth. From the perspective of someone on the spaceship, everything looks totally normal. The light travels straight up, hits the top mirror, and comes straight back down. One tick. But here's where it gets wild. What does someone on Earth see when they watch this spaceship zoom past? They see something completely different. To the Earth observer, the light isn't just moving up and down, it's also moving sideways along with the spaceship. So instead of traveling straight up and down, the light beam traces out this diagonal zigzag pattern. It has to cover more distance to complete each round trip. But, and this is the key, the speed of light never changes. It's always 299,792,458 meters per second, no matter who's measuring it or how fast they're moving. This is one of the fundamental rules of the universe, so if the light has to travel a longer diagonal path at the same speed, it takes longer to complete each round trip. The clock appears to tick more slowly. This is time dilation in action. The faster the spaceship moves, the more diagonal the light's path becomes, and the slower the clock appears to tick from Earth's perspective. At everyday speeds, this effect is tiny. You'd never notice it. But as you approach the speed of light, something dramatic happens. There's a mathematical relationship that describes exactly how much time slows down. At 10% the speed of light, time slows down by only about 0.5%. At 50% light speed, it's about 15% slower. But at 90% light speed, time runs at less than half the normal rate. At 99%, it's down to about 14% of normal speed. And at 99.9%, time crawls at just over 4% of its usual pace. As you get closer and closer to the speed of light, The time dilation effect grows dramatically. Actually reaching the speed of light would require infinite energy for anything with mass, which is one reason why nothing with mass can actually get there. Now here's where most explanations stop, but that's where the real weirdness begins. Because time dilation isn't just about speed, it's also about gravity, and this is where things get truly mind-bending. Einstein realized that acceleration and gravity are basically the same thing. If you're in an elevator accelerating upward, you can't tell the difference between that acceleration and being in a gravitational field. This insight led him to general relativity, which revealed that massive objects don't just bend space, they bend time as well. The stronger the gravitational field, the slower time moves. This means that right now time is running slightly faster at your head than at your feet. The difference is incredibly tiny, about 90 nanoseconds per year for a 6-foot-tall person, but it's real and measurable. This gravitational time dilation becomes extreme near massive objects. Near a black hole, time can slow to a crawl. If you watch someone fall toward a black hole's event horizon, you'd see them slow down and freeze, their image getting redder and redder until it fades away. But from their perspective, they'd fall normally. It's only your view of their time that changes. But here's something that trips people up. Time dilation is relative. Each observer experiences time normally from their own perspective. If you're on that high-speed spaceship, your watch ticks normally, your thoughts proceed at normal speed. Everything seems fine. It's only when you compare your experience to someone in a different situation that the differences show up. This leads to the famous twin paradox. If one twin travels to a distant star at near light speed while the other stays on Earth, the traveling twin will age more slowly and return younger than their Earthbound sibling. But here's the thing, this isn't symmetrical. The twin who travels has to accelerate, turn around, and decelerate. They change reference frames. The Earth twin stays put the entire time. That breaking of symmetry is what makes one twin younger than the other. There's also this mind-bending question of simultaneity. What does now even mean? Events that appear to happen at the same time to one observer might not be simultaneous to another moving observer. The faster you're moving relative to someone else, the more your definitions of now disagree. This isn't just philosophical hair-splitting, it has real consequences for how cause and effect work at high speeds. You might think this is all abstract physics with no relevance to your daily life. You'd be completely wrong. Time dilation affects you right now, in ways you probably never realized. Every time you use GPS on your phone, you're relying on corrections for time dilation. GPS satellites orbit Earth at about 14,000 kilometers per hour and experience weaker gravity than we do down here on the surface. Both effects change how time passes for those satellites. Without correcting for time dilation, GPS would be off by about 10 kilometers per day. Your phone's map would be absolutely useless. The satellites experience two competing effects. Their high speed makes their clocks run about 7 microseconds per day slow, but the weaker gravity they experience makes their clocks run about 45 microseconds per day fast. The net effect is that satellite clocks run about 38 microseconds per day fast compared to Earth clocks. This might seem tiny, but since GPS relies on incredibly precise timing to calculate distances, even microsecond errors would make the whole system worthless. Time dilation also explains why we can detect certain particles that shouldn't exist by the time they reach us. Muons are created when cosmic rays smash into Earth's upper atmosphere. These particles decay so quickly that they should disappear long before reaching the ground. But many do reach the ground because they're traveling so fast that time dilation extends their lifespans by a factor of about 10. From our perspective, they live longer. From their perspective, the distance to Earth's surface shrinks, so they don't need to live as long to make the journey. This has huge implications for future space travel. If we ever develop ships capable of traveling at significant fractions of light speed, time dilation will become a major factor in mission planning. A journey to a nearby star might take decades from Earth's perspective, but only years for the travelers. They'd return to find that everyone they knew had aged much more than they had. But time dilation also offers a kind of time travel to the future. If you could travel fast enough for long enough, you could experience months while decades pass on Earth. You'd emerge into a future you'd never otherwise live to see. It's one-way time travel, but it's absolutely real. Time dilation reveals something incredible about the nature of reality. Time isn't the rigid, universal constant we intuitively think it is. It's flexible, relative, and intimately connected to space and motion. The faster you move through space, the slower you move through time. The stronger the gravity you experience, the slower time passes. This isn't just theoretical physics, it's measured reality that affects everything from the GPS in your pocket to the particles raining down from space. Einstein's insight that space and time are woven together into space-time, and that motion through one affects motion through the other, fundamentally changed how we understand the universe. So the next time you're rushing somewhere, remember, you're not just moving through space, you're also changing how you move through time. You're participating in one of the most profound and beautiful phenomena in physics, the dance between space, time, and motion that governs everything in existence. Time dilation isn't just something that happens to particles in accelerators or satellites in orbit. It's happening to you right now as you move through this strange and wonderful universe we call home.